All right, everyone. Welcome to our presentation this afternoon. My name is Mike Ault. I'm the Oracle Guru for Texas Memory Systems. I'm also an Oracle ACE, and I've been working with Oracle since around 1990. You may or may not have seen any of my books if you're developers. DBAs probably have them sitting on their bookcase somewhere. I've written about 24 to 25 Oracle-related books, so hopefully I know something about what I'm talking about. At least I know enough to write a bunch any. So what we're going to be talking about today is legacy when you need a bigger hammer. And what we're talking about here, of course, is where does Oracle need speed? Oracle is very dependent upon the underlying storage and the caching that it has to perform properly. So we're going to take a look at where this will have a direct effect on what you do as developers and what can be done about it. We'll also talk about what does TMS offer Oracle to offer better latencies and better response time. We'll also show some examples, and then we'll have some time for question and answer. So where does Oracle need speed? Well, as developers, you need to be conscious of the speed of execution of your queries and your other application components. Nothing's worse than turning over your application and having people come back and make you rewrite and rewrite and rewrite. Speed of execution is directly proportional, of course, to the amount of the resources that you use within your application. Speed of execution, of course, is also dependent on available system resources. You may have done everything right in your code. However, if it doesn't have enough resources to execute, it's going to appear to be slow to the end user. So when we talk about tuning, what are we talking about? Well, an application code section is tuned when it consumes the least amount of all resources. This includes things like latches, enqueues, mutexes, locks or spins. If you're talking about the CPU, in the memory, minimizing cursor size, data requirements, temp usage, all of that. And of course, reducing the I/O per second, or IOPS. By reducing all of the resources that are used to their minimum value, the code will execute efficiently and quickly. So what do we typically do when we tune, of course? We look at the statements in the application and see where we can minimize resource usage by proper use of paths, by proper use of memory, by proper use of sorts, eliminating unnecessary loops and other pieces of things in the code that can cause it to be very inefficient. We add indexes to underlying tables to reduce the amount of I/O required. We may partition to reduce the size of large tables. We may use parallel query so that we can divide those larger tables or those partitions into manageable sections that Oracle can then use individual processes to handle and give back the results quickly. We'll also go in, of course, and look at do we have enough memory? Is the DB cache size correct? Do we have enough sort area in the memory to handle our sorts? Is there enough cursors being reserved? All of these things also add to the speed of execution. And of course, your sort and hash areas. When you do have to do necessary sorts, are you providing enough resources that don't have to go to disk? Because of course, as soon as you go to disk, you have lost your performance. And then OS tuning. Did we provide enough memory to Oracle to operate properly? Have we mounted the file systems correctly? Do we have the underlying I/O subsystem tuned properly for our application? And of course, then we'll say, well, maybe we don't have enough bandwidth. Maybe we're just not getting enough I/Os out of our system because it doesn't have enough pipeline between here and there. And so we may add things like NIC cards or HBAs or whatever to the server and to the underlying storage subsystem to try and make things go faster. Of course, what happens when you've tuned and things are still bad? Typically using physical disks, latency will bottom out at about 2 to 5 milliseconds. Now, you may say, but I've seen latency less than that and we're using disks. Probably what you're actually seeing is response from a cache, where they put either flash or some DDR type memory in front of the disks themselves, and frequently accessed read-only type items are put in that cache. And so that is naturally served at the speed of whatever the memory can provide, plus the speed of the interfaces that are connecting you. And so normally you may see 0.5 milliseconds or less from a cache. But of course, the problem with caching is that it can get flooded, and once you flood the cache, then any new items are going to be, of course, served at disk speed. Now getting back to disks, once a majority of your I.O. reaches that level of latency that can be supported by your I.O. subsystem, there's not much more you can do to tune it, because every new latency is going to be responding at that level. And of course, as you start stacking I.O. requests up against the SAN or against the disk subsystem, then you get into queuing. And what queuing then does, of course, is multiply that effect. And so now your 2 to 5 seconds goes to 5 to 10 milliseconds, goes to 10 to 20 milliseconds as the queue increases in size. And of course, as we mentioned, caching helps until it gets flooded. It's very difficult to cache the entire database. So what happens when this comes into play is you need a bigger hammer. You squeeze the last resources out of your physical I.O. subsystem that you can possibly do. In this case, what's killing you is the latency. And so you've got to do something to reduce that latency. Now, of course, you can add more cache to your underlying system. You could do other things that are bandage type things or Band-Aid, just trying to fix the problem. But until you actually replace that underlying system with something faster, it's not going to do forever what you want it to do. Of course, latency is called response time or wait time. And what goes on with that is it's the amount of time between the request that a resource is issued and when that request is served. To kind of put it in more layman's terms, consider a call support center when you call up support, for example. The latency is the amount of time the customer has to wait after dialing that the support person actually responds to you. So all of us have sat on that phone trying to figure out what's going on with Oracle, trying to figure out what's going on with Microsoft, trying to figure out what's going on with our PCs, our laptops, our servers. And if it takes 5 seconds for them to respond to you, we feel pretty good about it. If it takes 30 minutes, unfortunately, which is the usual, we're pretty angry that our time's been wasted. So again, the latency there determines how the user feels about your system and your application. So this latency is a critical factor in performance. It has a dramatic impact on the way that your clients see the code that you've developed. Again, you'll have a dramatically different perception if the service they wait for is 1 minute versus if they wait 30 minutes. So if they, an example I can pull from my history is I went to a place to do some tuning. They were a call response center essentially, where they were placing orders. And what would happen was the person would enter the person's name on the form, hit enter, and then it would take 7 minutes for the system to respond to them. And naturally that was a bad experience for them. They had to put up with the person yelling at them, fussing at them. And when we went in and added some indexes, tuned some code, did some other things to the database, we got that down to less than 30 seconds. And so that was a much better response time and much better latency for that particular operation. And that's what you hope to do by replacing. Once you've tuned everything else and all you're left with is the physical I.O. subsystem, you have to look at reducing its latency. Of course, there are several metrics that actually measure how your underlying I.O. subsystem performs. One big measure is the I.O.s per second. So if you've got a high number of I.O.s per second, you can utilize it to serve more clients, to do more work. However, each one of those will have their own latency, which we'll talk about in a moment. Bandwidth, of course, is the number of bytes transferred per second. In the industry, we've done a great job of increasing bandwidth. We've increased it 30, 40-fold over what it was from the beginning. Unfortunately, our underlying disk subsystems haven't kept up with being able to service that bandwidth. And finally, of course, response time, which is the amount of time each I.O. request takes to complete. So if you've got 1 million IOPS, but they're all taking 5 to 7 milliseconds, when you get sequential I.O., where they come one right after the other, you really haven't improved your performance. Queue depth, we talked about before, is response time times IOPS. So that gives you some idea of what your queuing will be. So the queue is the number of parallel I.O. requests that you can service given your IOPS and your response time. And this formula is known as Little's Law, and it can be applied to many different situations to determine if you're operating efficiently. Of course, sometimes you'll hear people claim that all they want is bandwidth. If you give me enough bandwidth, I can do this. I can perform well. Of course, if you really didn't care about latency or IOPS, how would you get the best bandwidth? Let's say you're going to a disaster recovery site. Would it be fiber channel, InfiniBand, dark fiber, iSCSI, or something else? Well, actually, in that situation, the maximum bandwidth would be a truck. You could put 10,000 1-terabyte tapes in a truck, move it to a remote site in 8 hours. That's 460 gigabytes per second of transfer. Of course, your latency is 8 hours, plus whatever it took to restore the tapes. So that would limit that type of transfer's usability. So again, all these things are related, but they're not tied together. You can get IOPS without having good latency. You can get bandwidth without having good IOPS or latency. So all these things need to be provided at the proper level for your application to perform. So if you don't just want bandwidth, how can you tell if latency is where you should focus? Well, one way is to look at your server statistics. And if your average queue depth is more than 1 or 2, then you're definitely seeing some queuing going on. If queuing is going on, you'll see your latency increase because the disks are not serving each request as soon as they get it. Another one is CPU utilization. It's how much time the processor are actually processing data versus waiting for data to process. So if you look at your CPU utilization and it's low and your I/O weight is high, that's a good indication that your I/O subsystem is not servicing all the requests in a timely manner. Generally speaking, if your average queue is 1 or higher and the CPU utilization is low, you have a storage bottleneck. But again, getting back to bandwidth, how to determine that bandwidth isn't the bottleneck that's causing the problem? Well, frankly, storage bottlenecks are rarely bandwidth related. Of course, you'd think with all the hype going on about things like the Exadata and some of the other things that offer, the 40 gigabyte path widths and all this stuff brought to you by InfiniBand, that's the major issue. But it's not really. I mean, the interface bandwidth has increased at a much faster rate than disk latency. From 1987 to 2012, bandwidth improved at least 30-fold, while the disk latency improvement was only 3 times. Remember, the disk latency is directly responsible, or pardon me, directly related to the speed of the disk drive. So we went from about 5,000 RPM disk drives to 15,000. That's a factor of 3 increase in speed, which means that the latency dropped by a factor of 3. Now, you can increase bandwidth, in other words, how much I/O you can do or how much megabytes you can transfer by increasing the number of disk drives. This will also increase the number of IOPS that you can serve. But we can't get away from the latency issues. The latency is still going to be at that 3 to 5 millisecond level. So, all this talk about latency, where does it really matter with Oracle? Well, let's take a look at this little graphic here. Let's say you issue a query. Well, that query has to go first through Oracle and then go out to the disk. Then the disk has to service that, and it's going to come back at that storage latency. So when you see things like if you're looking at AWR or OEM or some other thing that's reporting you back Oracle waits, and you see DB file sequential reads, DB file scattered reads, DB file parallel reads, direct read temp, direct read, these other type of waits, and their latency is exceeding this 3 to 5 milliseconds, then you have a storage latency problem. So reads are our major problem for our latency. So why don't writes matter in Oracle? Well, for data and index block writes, it uses a process that we used to call delayed block cleanout. And essentially what it does is it writes when it can't find clean blocks in memory. So it writes every 3 seconds, it writes on checkpoints, and there's several other things that may trigger it. But writing, at least as far as the data and indexes are concerned, is not a critical function in Oracle. Now, there are some files where it does matter. So when we do insert updates and deletes, in other words, do transactions within Oracle, where does the latency matter? Well, here we do a user insert. Now, remember, in memory, it's just going to hang out there. You can see that little blue dot up there. But the Oracle process is not going to finish that insert until what happens? Until it writes the log. Once it writes the log, Oracle considers that transaction completed. And then it takes its own sweet time with DB Writer to write the memory out, or write the memory contents out to the data or index where it needed to go. So you can see that logs have to be performant. So that's where write time makes a difference. Where else? Well, if you do a sort and it ends up going to disk, it better be performant. If you do a hash where you're doing some type of a join with two full tables, that also has to be performant, especially if it ends up going to disk. And any use of global temporary tables, bitmap indexes, if things aren't properly tuned or if there's enough resource to service it in memory, it has to go to disk. So again, all these type of writes are very critical to service very quickly. And of course, any non-memory undo activity. What do I mean by that? Well, Oracle uses in-memory undo since version 10, which means that instead of having to write every little undo action to disk, it only writes the critical ones. So it does all the small stuff in memory now, and then it writes out the major operations to disk. So it greatly reduced undo activity. Now, another place that performance is going to be important that involves writing is, of course, getting into the flash cache. Flash cache itself is actually two things that Oracle calls flash cache. There's the Exadata Smart Flash, and then there's the DB Flash Cache. The Exadata Smart Flash is a SAN cache made smart for Oracle. It sits down on their Exadata storage cells, and it forms a read-only cache. Of course, that memory can also be used as a LUN if you want to carve it out that way, but Oracle really doesn't recommend that. Now, flash cache itself is for flash or other SSD. We're talking about the DB flash cache, and it's used as an L2 cache for the DB cache. So essentially what happens there is when a block gets bumped, and this is not a dirty block, this is a clean block, so something hasn't been inserted, updated, or deleted to it, from the cache because there's not enough room, previously it would of course get written back to disk, or it would just fall into the bit bucket, and then you'd have to reread it from disk when you needed it. Well, now what happens is it falls into this L2 cache if you've got the flash cache option turned on. Of course, the flash cache is only available under Solaris and under Oracle's Linux. Now, Oracle suggests at least a 2 times the DB cache size for the size of this thing. In my testing, I didn't really see good results until starting getting up to about 4 to 5 times the size, or even up to 10 times the size. So you need quite a bit of cache out there to make it useful. So where can you put this? Of course, we've got 2 products that do this very excellently. The RAMSAN 70, which is an internal PCIe card, and we've got the RAMSAN 440, which is an external attached DDR. Of course, it's a lot more expensive because it's DDR, but to get the speed that you need to respond, we'd recommend using that if you're going to do it externally. Of course, you could hook up to our external flash units, our 710, 720, 810, 820, or 630, but they wouldn't give near the performance probably that the 440 would. Now, what does flash cache give you a benefit? When would you want to use it? Again, if you can't size memory enough, you can't get enough memory resource, but you can put a flash card in there, then putting the flash card in there and assigning it to this flash cache would give you some performance boost. You can see here that we boosted our performance by 30–40% just by adding in the cache and assigning the tables to it. So what does TMS offer Oracle? What type of hammers do we offer? Well, we've got the 710, again the 720, the 810, we've got the 820, we've got the 630. Redo logs, you can either go to like, for example, a log LUN on our older boxes, or you can go to our new environments. We've got the 512 native write, which makes them very performant. So again, if you didn't want to use flash, you have the 440 or the 70 internal card. Of course, if you've got a rack environment, you have to go with external storage. Flash cache itself, as we said before, the 70 to the 440. Now all these numbers probably going, so let's take a look at some pictures. So there on the left, we've got the RAMSAN 70, which holds up to 900 gigabytes of memory. We've also got the 710, 810, which goes between 5 to 10 terabytes of flash in a 1U box. Then you've got the 720 and 820 that goes 12 to 24 terabytes of storage in a 1U box. And then the 630, which uses what's called SLC flash. And it provides 10 terabytes of storage and up to 1 million IOPS. Its biggest offering is that it offers 10 interfaces on the back for you to plug in, whether they're InfiniBand or fiber channel. You notice that the IOPS on the RAMSAN 710, 810, 720, and 820 are limited to about 400 to 500 IOPS. This is because they just don't have as many interfaces as the 630 does. Anyway, most of the time you're not going to have any need for near that many IOPS. I think the highest I've seen so far was about 50,000 IOPS in one application. So let's take a look at some examples so you can understand what I'm talking about here. The TPCC test, of course, is used to do OLTP type operations. In other words, any small transaction where there's lots of small transactions going on, this is meant to model it. Now the TPCE is replacing it, but for now people are still using the TPCC quite a bit. And what this particular graphic is showing, these 4 bottom lines are going to a standard disk array. And this is 1 node, 2 nodes, 3 nodes, 4 nodes in a rack cluster. The top 4 lines are the same thing, only with the same exact database, same settings, except storage has been switched over to, in this case, a RAMSAN 630. So when we look at the performance, we can see that 1 node running on a RAMSAN outperforms 4 nodes running against disk arrays. And of course, we get much greater performance at the 4-node level than what we see at the 4-node level with disks. So again, by replacing that low or high latency disk solution with a low latency flash solution, you have provided usually much more performance than you could from tuning even. So it's another case where if you're stuck with a third-party application that you really can't do any tuning with, you can improve its performance considerably if it's I/O bound by replacing the I/O subsystem with a low latency one, such as the solid-state devices. Another example is the TPCH. This, of course, is a decision support and data warehousing type of application that consists of about 22 queries that you run, and basically you're just looking to see how fast does it run these queries. And so you can see here that if the query itself is CPU dependent, we don't get much improvement. But when you get one that's very storage dependent, like indicated here, you can see that in this case we've got almost a 20-fold performance improvement. So again, when you need a bigger hammer, that's what we provide. Some additional testing using a single HP server here recently, and then running with a single RAMSAN 630 with a log run. First, we tuned the cache, so you can see that we got the cache up to 40 gigabytes. Then we did various different tuning operations. And I don't know if you paid attention on another graph, but we peaked out at about 3,500 transactions per second. Here, we're doubled that with a single node. So we got 7,000 transactions per second. And this was just a particular test where we the example schema we're using single table clusters and multi-table clusters. And in our testing, we determined those really weren't needed with Flash. As you can see, with no clusters, it actually performed much better. So how does the RAMSAN actually help in these situations? Well, going back to our reads diagram, the user pumps a query in, and now it's being fed by the RAMSAN at SSD latency. This SSD latency, of course, is anywhere from 10 to 20 times faster than the disk. So now instead of taking, let's say 3 milliseconds, it takes 0.3 or 0.2 or even as low as 0.1 milliseconds to be served. So you can see that now that performance is not based on the underlying storage. It's now based on how well the query has been tuned and how well it operates. Now with writes, what we did in this particular test was we put a mirror inside the RAM sands, and then we took that mirror and wrote all of the logs, temporary, and undo to it. So now what happens, of course, is the user does an insert, and now when the log write goes out, it goes out at SSD speed. So with that going to the SSD, we're able to greatly improve the number of transactions we can get. And then eventually DB writer writes, and because what we did here was do a preferred read mirror out to the disks, the write speed was actually limited due to the convoy effect to the speed of the disks. But one thing this hybrid type configuration does for you is provide the certainty of the disks there as far as the data, and also allows that data then to be easily transferred, for example, using SRDF or whatever, to a remote site for backup. So why should you as a developer really care about all this? Well, Oracle is becoming more self-tuning every day and becoming more hands-off. Now, in some cases that's a good thing, in some cases it isn't. For example, there are certain weights that will be increased if you increase the DB file multi-block read count. That's one of the parameters the database administrator tunes. Now it's gone into auto-tuning, and if it jumps from 16 to, say, 128, especially in a rack environment, you can get some very nasty weight problems. So knowing what Oracle auto-tunes and what have you, you have to kind of walk a tight wire there to see whether to let Oracle tune something or not. So once these internal resources that Oracle has control over, CPUs used, memory, the number of IOPS, Oracle can't do much more unless you go with the full Exadata route, which even then, once you get past its bells and whistles, it's limited to disk latency. So I/O is the final hurdle to best performance. By releasing or reducing that latency in your disk subsystem to the absolute minimum, or in this case your storage subsystem, you'll get the best possible performance. So reducing latency is the key to tackling these I/O issues. All right, so now it's time for questions. I haven't really seen any come up, but go ahead. Okay, there is the raise your hands button there if you want to, raise your hand to ask a question. All right then, well, thank you all for coming in and watching the presentation. I hope you learned something from it, and feel free to email me or Kelly with any of your questions that you may come up with afterwards. You come to our website, and of course you can download any of the material on any of the systems we talked about here, and there's also plenty of white papers out there that you may find interesting.